Hello and welcome to the final session of the MakerBot Pro Summit. My name is Shawn Miely. I'm the Director of Marketing at MakerBot, and I'm really excited about this topic: healthcare innovation, advancing humanity through 3D printing. We've actually, a lot of people have probably who are familiar with 3D printing have probably seen some of the promises that additive manufacturing and 3D printing have in the medical space and healthcare. A lot of times you see it in the operating room with surgical models based off of somebody's specific anatomy, or in another case, maybe in a lab, they're using some kind of research bioplotter, bioprinter to try to print an experiment with printing human tissue. Those are two kind of popular in the media stories. But additive actually expands well beyond that in the healthcare industry, from product development on the medical device side to what we'll be talking about today, the R&D and drug development side. And so I'm really excited for our guest who's going to be speaking in a few moments, Milde. He's a senior scientist in discovery sciences at Pfizer. He's got over 17 years of experience, and he's going to be talking about how they've used the MakerBot method and 3D printing to automate and kind of optimize their drug development process, which is actually a really cool thing that I didn't really know much about until recently talking with Lane. So without further ado, Lane, glad to have you here, and I'll let you take it away and go ahead and share your screen there.
Thank you, Shawn. It's great to be here. Thanks for inviting me. I'm looking forward to sharing some of the exciting things we've been doing with our 3D printer at Pfizer. So I'll start out, just kind of came up with the three different kind of ways that we're utilizing our 3D printer to help us make life easier in a very highly automated pharmaceutical lab. Our primary objective at Pfizer in R&D is to develop new therapies for patients, and the group that I work as a part of is very involved in the extremely early part of the drug discovery process. And so I'll start out by giving you a little background about myself. I'm a senior scientist, like Shawn said, at Pfizer. I specialize in automated liquid handling and laboratory automation. And the specific department that we work in within Discovery Sciences organization is compound management and distribution. And compound management is really about screening a very high number of compounds to develop lead material for potential therapies, or to help us learn a little bit more about mechanisms of action in a particular target that we may find interesting for therapeutic development. So I've spent about the last 17 or so years working in a variety of highly automated laboratories in the academic, biotech, and pharmaceutical industries. I started out, I grew up in Wisconsin, and I went to UW-Madison. And after that, I worked in a couple of labs at the university, one of which was a core facility that was involved specifically in high throughput screening and performing high throughput screens. And it was sort of a one-stop shop for compound management and screening for end users who are usually grad students or PhD postdocs that would be doing these screens. So we worked closely with them to perform those. Outside of my work, I like to snowboard, go to the beach. I like to travel and spend time with my family. But in my workspace, what really gets me excited is being able to make things easier to get done in the drug discovery process. So like I said, we're very early in the stages of this process. I have a little graphic here that shows kind of what what the overall process timelines might look like. And I want to show you that our part in this process is probably just this vertical line, uh, which is really, it extends a little bit into this you see 10,000 number. And these are relative numbers. Pfizer has an extremely large compound collection, probably one of the largest, perhaps the largest in the industry, of several million compounds. And so these molecules, these compounds are could be any molecule. I have a few examples here: ibuprofen, omeprazole, two very common medications, and you can see basically our molecules are all just various organic structures that can be run with an assay with the reagents that they can then determine if that has any activity against their target. So any molecule that becomes a lead pushes further into this process. And you can see that the timeline is very extensive. So a lot of what we're working on doesn't even generally get to the clinic for 5 to 10 years. You can see clinic, they're narrowed down to a very small number of compounds because this gets very expensive. And if you're lucky at the end, you might get one FDA approved drug. So a little more specifically about what we do in compound management is really to hold and maintain the physical liquid compound collection. And we provide those samples by request for researchers that they may be running in their experiments. Now, our responsibilities don't just include delivering the physical samples in the exact volumes and formats that might be requested for the specific research that is being done. We also have to provide that data that allows them to analyze the data for potentially millions of rows of data and tell them what the important information is, which compounds are they going to be interested in following up on. And then our third and also a very important function is maintaining and measuring the integrity of the samples. And so one of the ways we do this is we store our samples in a large automated store. So here's an example of one. This is actually our brand new store that we purchased that goes with this tube. It stores millions of these tubes, each containing an individual sample. And each tube is barcoded. You can see a 2D barcode. This is a special kind of barcode that actually is split into two, and there's software that compare this back up. And the reason for that is this black square-shaped area in the center needs to be completely free of any variation in thickness. And this small printing actually increases the thickness and interferes with the dispenser, which uses sound waves to transfer nanoliter volumes out of these tubes and into these types of labware that might be used for a downstream experiment. So these are what we call microplates, and they come in a variety of densities. So you can see on the left side, you can see one that's a 96. That's an 8 by 12 array, and then they go up in multiples of 4 from there. So each well would be divided into 4. So you have a 96, and you have a 384, and then you have a 1,536. So you can imagine that if someone is testing a million compounds, that being able to do that in 1,500 at a time saves them immensely, not only time, but also reagents, and just gives us the ability to do that in a more conservative way. So one thing that I couldn't talk about compound management without mentioning is automation. So my main function is to support, design, and keep all of the automated systems in compound management running to be able to meet our turnaround times. So we have a variety of automated systems, and Some of the smaller ones may just have a single robot and one device and labware storage, where it would just move the labware to the device and back to storage in order to process a number of those microplates in a run. The system here in the picture, and I have a video, is our largest automated system. You can see there are 2 robots. There are over 25 different peripherals on this system. You can't see them all in this video. There are some that are off of the frame. This system actually has 4 cameras mounted on the ceiling that allows us to do remote troubleshooting and root cause analysis for failures. One of the main things we analyze is the robotic teach points. So the robots may crash. They may have an incident where the system stops because a teach point needs to be adjusted. And so one of the things that my group does is maintain those teach points so that our system can run smoothly. And you can see this system is very complicated, and it requires a lot of attention in order to keep it running at its optimal pace. So to move on to the meat, how are we using 3D printing in our labs? I've kind of narrowed it down into 3 sort of categories. One is rapidly being able to prototype an improvement for some automation component. And that may just be a prototype, and we may send that design out to a machine shop that we partner with to make them out of a stainless steel or sometimes aluminum, depending on the application. Now, the second category is hardware components that we can directly implement and directly place into an automated system to solve a problem. The lines between those first 2 are starting to be a little blurred, which I'll get into. And really, that's a result of the ability to use carbon fiber in our 3D printing process. And then the last category is just manual tools that we might use that can supplement the use of our automation. There's always cases where some manual intervention needs to happen, and sometimes there are tools that could make that manual processing a little bit easier to get us back into being able to use the whatever it is fully automated. So the first kind of show and tell I wanted to show you about kind of what got us into 3D printing in the first place in our labs was an issue that we had with that system I just showed you. The original design of the gripper shown in this photo right here. You can see the pointed contact points where it makes contact with the plate. You can see them in this angle as well from a top-down view. And what we found was that over time, repeated gripping, because these source plates have 1,536 compounds in them, they may get used many times. Somebody may place an order for a set of compounds, and there's one on this plate. And then somebody else may place an order for a different set of compounds, and one of those is on this plate. And so as a result, the plates were being gripped so frequently and repeatedly that these points were actually boring a hole through the side of the plate over time. And what that would do was cause the gripper to misalign, and it would hang on to the plate and not drop it, and cause the plate to fall onto the floor, and we would lose the contents of that plate, which is time consuming to remake, or if it's even possible, and costly. So in order to solve that, we went back to the design, and we copied the design of the gripper and just modified these contact points. And you can see we have this different geometry here that allows a secure grip, but spreads the force over enough surface area that it's not causing damage to the plate. And you can see here we did our initial design, we 3D printed as a proof of concept, and then our final design was sent out to a machine shop to be made out of stainless steel. And you can see here's the robot with its new grippers. And then we also in order to be able to maintain those teach points that I was mentioning, we designed a customized teach plate that would interact with these contact points, so that you can simply place this plate in one of the nests, drive the robot over, close the gripper, and if the points nest inside these cutouts, then you know you've taught the position properly. So our 3D printing setup, we were able to, because of that project that I was just telling you, that was done about a year to a year and a half ago, we were able to justify with some remaining operational budget in late 2020 to purchase the Method X Carbon Fiber Edition. So um, then I went on and I hired a summer student for this summer as part of the Pfizer Summer Worker Program. It's a great program if you aren't aware of it, open to incoming college juniors and seniors. And um, there are a variety of different um, positions that can be had, everything from IT to chemistry, and even unique stuff like what I have here, which I don't think has been done for an internship at Pfizer before, but could end up being an ongoing thing based on the success that we're having so far, and I hope we continue to have. And we've used a couple of different design software programs. We've used Fusion 360, but more recently we switched over to SolidWorks. We think that gives us a little bit more power in terms of what we can do, although we're probably not using that to its full extent, at least yet. And then one thing I also wanted to point out is we don't reinvent the wheel. We like to, if there's something we can use to solve a problem readily available, like on Thingiverse, there are so many designs. We like to try to build off of that instead of spending our time reinventing something that may already exist. So as far as hardware components that we can directly use to solve workflow limitations, this is a particularly exciting space for me, just because there's a lot of potential for rapidly solving problems and saving very large costs involved. And so those acoustic tubes that work with that acoustic dispenser that I showed in the picture have a screw cap. So the cap needs to be screwed on and unscrewed in order to seal the tube and protect it from the elements. So we have this automated system which decaps and recaps 96 or an entire rack of 96 at a time. And the issue with that, and I'll show you this video, I've sped it up a little bit just for ease of viewing. This cycle takes about 30 seconds or so to run that cycle. So you can see I've sped it up about 3 times. And you can see what this tool we made does is it mimics the geometry of a rack. It has the same 96 hole and thread pattern that a rack of tubes would have. And it allows the operator to tell this instrument to recap, but place this in the instrument instead of a plate, and it will recap onto that, thereby freeing the instrument for them to run another one and decap a second rack. So this is a big deal for the process that we're currently running to fill these millions of tubes with the samples, because the source labware is a 384 format. So in order to run a single run, we need 4 of these decapped at the same time. So that's what sparked this design. Now we did a little brainstorming and we figured out, well, we could buy additional decapper units at $70,000 each. We could sacrifice acoustic tube racks. That would give us substantial savings over additional units at $150 a piece for the tube rack to use instead of this. But we found that we can make these, out of tough material, we can make these. And that only costs us about $9 each, which is actually probably one of our more expensive prints because of the how much material there is in this in this design. So another kind of a neat hardware component that we built that solved a problem immediately for a scientist running an experiment was that they were running this in a 1536 wheel plate, and you can see this picture is the bottom of the plate. And we ended up designing this frame that fits inside here and just kind of hugs this bottom that it surrounds the wells of the plate. So the problem that they were having was they had a run of about 20 of these in a stacker, a labware stacker, where the plates are just stacked one on top of another, but there were liquid in the plates as part of the experiment. And due to the geometry of these, it actually creates a very nice seal between the bottom of this plate and the top of the plate below it. And so condensation will kind of happen and create a vacuum. And what was happening was they were seeing two plates being pulled out of the stack at the same time, which was causing a crash with the automated liquid dispenser that they were using. And so we designed just this frame that allows this edge to be raised up off of there a little bit. And so this doesn't make such nice contact with the plate below it anymore. And so the evaporation is allowed to kind of freely evaporate rather than kind of creating that seal and suction there between the plates. And then another really related to that, actually, you can see the racks of acoustics tubes here. This is a plate hotel that is part of the automated system from the video. These can, in their maximum configuration, hold about 1,000 microplates, but there are times when the end users need to actually remove an entire stack from this. And what they do is they have to pull this stack forward and tip it at a slight angle towards them in order to release it from its mechanism that holds it in place. And so it becomes a little bit of a trick with the operator using their hand to hold the plates in and keep them from falling out while they're doing that. And so we designed a safety mechanism that utilizes an aluminum rod and two 3D printed clips that are held together by the rod and clip around this, and then you can squeeze to release it and move it to the next rack so that you can use a couple of these can allow the operator to replace all of the stacks on an Ambistore with different stacks containing different labware if they choose to do that. And then in the space of manual tools that we use to supplement our use of the automation, we're still talking about the same acoustic tubes. And there are times when the user needs to manually decap or recap a tube. And what we found is that the variable torque that's applied just using a regular driver to tighten those caps causes the automated decapper to malfunction. And so what we did was we actually reused the concept from this design, this NASA wrench from Thingiverse. And what it is there's a slip gear in here that allows the mechanism to slip when a certain amount of torque is applied. So it maxes out the torque at a certain value. In this case, it's a 3 inch-pound, you can see. And so I gave my student this challenge to basically take this design concept and build cap the tube, but limit the amount of torque that they can use. And so it will be very consistent torque across the tubes and hopefully give the decapper a better chance at being successful. And then another one that we did was recovering the contents of one of those 1536 well plates. And you can see that this has a frame around the outside. That's a 3D printed frame because the skirt, which actually sits right underneath that and goes around the plate, was broken in certain places. And in order to replace that plate, we wanted to transfer the contents to a new plate so that we could save those contents and not have to either remake them or tell our downstream researchers that they can't have what was in there. So in order to do that, we designed this frame that helped it sit correctly on the nest of the automated tip-based dispenser that would align 384 tips in a spread across this. And so 384 tips in a pipette head would go down. So it needs to be very well aligned. And there was enough play without the frame that we just couldn't do that process. But with the frame, it allowed it to engage with the positioners on the liquid handler, and we were able to recover those contents. So this frame and the other sort of frame that I had are really great examples of a very fast solution. So that's just something that without 3D printing, if we could do it at all, it wouldn't be anywhere near the pace that we were able to do this. So we were able to print this in about a half an hour and in the same day recover those contents. So that's just something that without 3D printing we wouldn't be able to do. And just a couple little ideas that we're working on right now in the works is trash chute. So this allows a larger trash receptacle to be used to be able to support longer runs on an automated tip-based liquid handling deck. So it's kind of a slide where the head will eject the tips and they'll slide at an angle off to the side of the table where they're sitting, and we can use a standard trash receptacle to collect that then instead of a smaller bag. Something that I'm excited to try is this dual material non-slip instrument feet. So you can see this would be made with a PLA or a tough material that would sit next to the instrument, and then at the end of the foot there would be a flexible material that would allow or it would actually not allow the instrument to slide around as easily on the bench, because we found that our hard tabletop surfaces allow the instruments to slide around a little bit and make it a little bit more difficult for repeated use. And so I just wanted to also mention that we've found over the years a lot of people customizing their own tools. You can see a great example of that here, where a rubber band was used to add some flex to this Allen wrench and also extend it further. So we've, as part of the internship that we're doing, we have created a request form using Microsoft Teams. We built a page where any scientist can come in and describe a problem that they're having. And if they have some idea of a part that may be able to help them eliminate that problem, or if they don't have an idea and they just have the problem and are wanting to brainstorm, they're able to use this form and they can submit a request to us, and we can then start a conversation and work with them to see if we can fulfill their need. So with that, I'd like to thank Evan Bean, my summer student, who's done a lot of this work, and my manager, Travis Mathewson, who has supported our 3D printing endeavors throughout. And then from MakerBot, Rosemary, Shawn, and Alejandra, I want to thank them as well for putting this together. So thank you, and I'd be happy to take some questions.
Awesome presentation. And
thank you.
Thank you, Lane, for joining us today. We're, like I said, super excited to to hear how Pfizer uses this, and it was even more interesting than I could have expected. So great presentation.
Thanks.
So we'll go ahead and get into some questions now. So first one right off the bat, there are a lot of kind of combinations that you guys do, or you're starting. You said over 10,000. You have millions of different of compounds. So how do you start? How do you even start? I mean, I feel like you must narrow it down initially with kind of some estimations of what might work better, right? You're not testing every compound you have, or
Absolutely, yeah. So a lot of our compounds are put into what we call subsets, and there's specific groups of molecules that we think already have, or we know already have an effect in certain therapeutic areas. And so we're able to do, in many cases, a very targeted screening approach. There are still some where they don't really have much of an idea. We kind of compare that sometimes to golfing blindfolded in the dark and trying to hit a hole in one. The more balls you hit, the better your chances. So
yeah. I mean, on that note, with the level of automation you do now, how was it done before automation tools like this? And I mean, that seems like you must have needed a lot more people, bigger
a lot more
labs involved
people,
in both.
yes, a lot more people. Things were much slower, and probably they cut more corners in the past than they do now today, especially. A lot of the approval processes and auditing and that kind of thing are much stricter today than they have been in the past. And so
Gotcha.
automation really allows us to maintain that integrity of our work, I think.
Okay. Just be way more efficient and
Yeah.
effective.
Yeah, that, and
Um,
we've reduced a lot of repetitive motion injuries too. I mean, you can imagine someone using a hand pipette to fill one of those
God.
plates, and to that, to that fact, it's things were done in much higher volumes and lower densities, so you never really saw people trying to put nanoliters into a 1536 well plate in the past
Yeah.
without robotics and automation.
That's crazy. Yeah, it makes sense. As a former biology student, I appreciate the automation side. The pipetting seems like it would be intense. All right. Let's see. Do biologists screen in 1536 or in 384 well plates? Somebody asked.
Sorry, could you repeat that?
Somebody asked, do biologists, or do you, I guess, screen in 1536 or 384 well plates?
Yes, yeah, both, and
Both.
96. Yeah,
Okay.
those three are our primary. There's even other densities of microplates. There are 3,456 well plates that
Okay.
are used very rarely. Um, while some of our systems do have the capability of working with those, there's very few instruments out there that are able to work with them, and so usually they aren't really used in normal research projects.
Gotcha.
1536 is pretty sufficient, and they're doing a lot of cell-based experiments and things like that. That once you get down to a volume that's less than a microliter, you have some different dynamics at play that may not be preferable for the experimentation.
Gotcha. All right. Next question was, are there any concerns with using PLA or tough materials in these testing jig applications, or are these strictly for prototyping?
For the most part, they're strictly for prototyping. Although, for one example, the cap holder is just made out of tough material. We do think that over time we've seen some very slight shrinkage of the material, and so that has had a slight effect. Other than that, we would generally not use PLA or tough material where they may interact with a solvent or anything like that. But for the most part, these are, I think, just tools that we can essentially throw away when they stop working for us and make a new one. So, I think in general, we don't have that many concerns, but as far as some of the more chemical resistant materials, we haven't played around with that very much yet, but we think in some cases there may be other materials that we may use, but for the most part, we haven't dove into that yet.
Great. Yeah, somebody else was asking to expand on that for IC50S or IC50s.
Yep.
So I assume it's the same kind of answer. They're not really coming into contact with.
Yeah. So, yeah, I guess I'm not sure what specifically the question about IC50s is, but that's something that we do really readily in compound management. So, our liquid handlers are set up to build primarily single point and IC50 plates. And so researchers usually will, when they have what we call a hit in an assay, they'll follow that up with an IC50, which is usually somewhere between an 8 and maybe 10 or 11 point dilution series that they'll do, which will help them determine the potency of that compound in their experiment.
Gotcha.
But we don't really use 3D printing directly in that process, more to supplement, like the stacker, for example.
Mm-hmm. Right. The plates themselves are made of a manufactured material that is chemical compound resistant.
Yes.
All right. Somebody wanted to know, what were your key reasons for choosing the MakerBot method?
Sure. Yeah. Well, a few key reasons, but I had actually narrowed it down to probably 3 3D printers that I thought could meet my needs. And the ultimate reason, I don't know if you'll like this answer, but the ultimate reason I went with the MakerBot is because of the price. So there was a special promotional deal at the end of the year, which the timing just worked out perfectly, that it fit under. We have a capital threshold purchase limit. And the other 2 instruments that I was considering were just above that limit, and that triggers the need for a vice president to approve that purchase. Whereas the price of the MakerBot, I was able to purchase as a lab supply, essentially, under the expense budget that we had remaining.
Awesome. So, yeah, no, I think that's a really good point with the method. It is, the materials you can use with it, the technologies that it has built into it. It's a really good value. I think it actually does a lot of the functions that you see with, $50,000 3D printers at like a $5,000 price point. So,
right.
I mean,
absolutely. I would echo that, in that, we don't regret our purchase in the slightest. I think we've got a ways to go to push the limits of this thing and try out its full capabilities, but so far, it's really meeting our needs, and there's a lot of potential to build more use cases down the line. So,
what kind of mindset do you have to use 3D printers, and kind of, I feel like you guys are always looking for a solution. You're always finding a problem, looking for a solution, or looking for problems, finding a solution. You've hired summer intern who is probably thinking through these things, but I feel like some companies asked this in the automotive session at the beginning of the day. Some companies struggle with like a kind of figuring out a problem to solve almost,
Yeah.
you know?
Yeah, that's a great question. I think, I'm in a pretty unique situation in my role at Pfizer. The problems kind of come to me. I built enough of a reputation as kind of just a outside the box thinker that when people have some unusual issue with uh, running an experiment, automation related, or something along those lines, that question will eventually find its way to me. And then, lately, what we've been doing is brainstorming if there's some way we can use the 3D printer to solve it. Until then, a lot of our problems we were trying to solve with off-the-shelf types of purchases, or, maybe in some cases, our local machine shop building something for us. But
Gotcha. I mean, you shared a bunch of applications that you guys have already come up with. Are there more? Like how many things how many projects have you used it for?
yeah, that's probably just the tip of the iceberg, I would say. We at this point have more ideas than we're able to do anything with, or at least we have a backlog of ideas that will probably take us beyond the tenure of my summer intern, and maybe into next year. And I imagine that the more people that learn about what we can use this for at Pfizer, the more demand we'll have. So
Speaking of internships, you mentioned it a couple times. I've gotten a couple questions. How do you, if we have a student who wants to apply for an internship, where do they find that? And do you guys accept
sure.
engineers as well as, I guess,
Yep.
more like science based?
Sure. Yeah.
Okay.
Yeah. It's really. I mean, the program is very extensive. They're like I said, you could be IT, computer science, biology, chemistry, even financial. Different. There's a wide range of different types
And
of
that would just
opportunities that we have.
and that would just be on the careers page for
Yeah, I think
Pfizer.
so. I usually get a link sent to me. I want to say November or December, to that's soliciting for job descriptions. And then I think towards the end of the year, in the January, February timeframe, it opens up for applicants.
Mhm.
So
Cool.
if you're interested in going to be starting your junior or senior year in college, then I'd put a reminder on your calendar. If someone is really interested in this, I would encourage them to reach out directly to me. Shawn, if you want to facilitate that, I'm fine with that. I
Yeah,
can
sure. No problem.
I
Just
can
email.
yeah,
You can probably find Lane on LinkedIn, but you can
sure.
also just email us hello@makerbot.com, and we'll definitely get any requests over to Lane as well. All right, so I think we're out of time here, but I guess I just want to end on one note. Like, what's kind of the future of 3D printing for you, for the Pfizer as a company? Are you guys just scratching the surface? And I guess any final words you want to share as well?
Yeah. I mean, I would say, yeah, we're definitely just scratching the surface here. It's 3D printing in these applications. I would say is sort of in its infancy. We're not really manufacturing anything. It's really just a way for us to really quickly solve problems that we encounter in doing our normal day-to-day work. So um, I think in the future I would expect that to really expand. I don't foresee us changing our approach. I think that um, in general we'll be just solving the problems as they arise, prioritizing things based on what the most critical projects to get through that discovery pipeline would be.
Awesome. Well, once again, I want to thank you, Lane, so much for joining us today. I want to thank everybody else who tuned in, people who have been with us since 9 a.m. this morning. Hopefully everybody enjoyed the second annual Pro Summit. And if you have any questions or any interest in MakerBot, you can email us hello@makerbot.com, or you can check out our 3D printers. The one that Lane was talking about, the Method Carbon Fiber Edition, go to makerbot.com/carbon. Check that out. I think we've got a kind of a little a promo going on with some free carbon fiber filament thrown into the package there, wrapping up this month. So check that out. And yeah, Lane, thanks so much for chatting today.
Yeah, thanks for having me.
Awesome. Thanks, everybody. Have a great rest of your day.